As I've mentioned already with significant figures, the main point here is that when we go to do calculations, we're going to be limited in how certain our answer can be. Frequently, it's described as a way to round. How I would describe it is it's a way to decide where to round. You're going to follow your normal rounding rules, but significant figures tells us where we should round our answers at. And then we have to have something in place of that since it's not a number after the decimal. And so then we are technically rounding the 56 there up to 60. Or in other words, we have a placeholder 0. Now that placeholder 0 is insignificant. We follow our sig fig rules. We've already determined that that's insignificant. If you turn it into scientific notation, you can show that that's insignificant there. Though, as I've said, without a decimal, it's not significant. If we are instead only rounding to 2 sig figs, then this one here is going to round to 8.4 there. And I will point out I'm going back to the original here to do the rounding and not this one. It should follow the same because for the most part, we've kept some semblance of the digits out here by the rounding there. I'll show you an example here in just a second where that doesn't work and why we should go back to the original number here. Anyway, 2 sig figs, we're going to have that 14 there. The 7 is going to cause us to round up to 15. And then here, we come back to this one, and 2 sig figs is the 3-2. The 5 is going to cause us to round up to the 3-3. There. And then again, we have to have the placeholder zeros, which are insignificant unless they're locked in by a decimal, and we can show that by writing it in scientific notation. And just for a cascading example, I'm going to use 746 here. If we round that to just 2 sig figs, then that becomes 750. If we then use that answer to round to 1 sig fig, then the 5 is going to cause the 7 to round up to an 800. Whereas if we round directly from the original to 1 sig fig, then the 4 is going to cause the 7 to not round, or we'll say we round down from 746 to 700. And so obviously there's a difference between these two here. And so personally, I always go back to the original number for more accurate rounding. I'll also say that if I'm working out a calculation and it's got 2 parts to it, but I need to report an answer in the middle, then that answer in the middle, I will round using a sig fig rounding rule. But when it comes to continuing the calculation, I personally will come back to this one and use it, or really just the answer function in my calculator, to start the next calculation, and then I'll round that answer to using proper sig figs. What can happen if you use this rounded value is this kind of cascading thing where the rounding one time caused additional rounding another. Personally, I'm going to take either. If you use your rounded sig fig answer, that's fine, though I think it's a lot easier than retyping a number in your calculator to just use the answer function. And using that answer function, you're going to be using the unrounded value anyway. Report your answers to any step in the problem that you have to report using proper sig figs. But when it comes to doing a new calculation with that old value, I personally always go for the original one so that we don't end up with that cascading effect. Quick practice problems here. So this one here, we want to go to 3 sig figs. So that's going to be 3.15, and to 2 sig figs, it's just going to be 3.1. And again, to 3 sig figs, so that's going to be those, so 825 centimeters. 3 sig figs is going to be those, so 0, because that leading 0 is insignificant, 112 grams. And 3 sig figs, we're actually going to have to add a digit here. And this is like when you estimate that last value on a measurement, you have to add in that to emphasize your precision. And so you'd actually round that one, or add the invisible 0 to give you 3 sig figs. When we are doing a calculation, then anytime you're doing a calculation that involves numbers with different levels of significance, then when you get an answer, and you'll notice this is just one of those long answers that you'll get on a calculator, you already know that your calculator is actually rounding that last value there, so even that's not precise. If you were to work this out by hand, you'd get even more decimal places there, and it's possible this one doesn't end. I don't know. I've not worked it out by hand, but you can see this becomes nonsensical to write. What we do is we always round to the one that has the fewest sig figs. So the 2.8 there has 2, the 67 number there has 4, the 30 number has 3, which they've already written out for you down here. So the fewest is 2, so I'm going to round my answer to the just 2 sig figs. Personally, I always use the squiggly equal sign to indicate that when I'm showing my work. You, of course, don't have to, and I'm totally fine with you without you writing this and just reporting the final answer straight as the rounded sig fig answer of 5.4. But we always round to the one that has the fewest number of sig figs. So now we have this problem, and unfortunately you're not going to get to see how I type it into the calculator, but I'm going to drop those zeros when I do it. I'm just going to do 5 instead of 5.00 because it's going to come out the same. 5 times 4.08 divided by 2. And I get 8.52 when I do that on my calculator here. And so 8.52, I then have to round to the one that has the fewest. That has 3, that has 4, and that one only has 2 sig figs. So I'm going to round to 2 sig figs. That's going to be the 8.5. The 2 means I don't round that, and my final answer is going to be 8.5. Like I said, I like to do the squiggly equals there, and then I always like to mark my answer there. So the rule for addition and subtraction is a little different. Personally, I was taught differently as well, but we'll stick with what the textbook says here on this one. But the rule is slightly different for addition and subtraction, and that rule is that we always focus on the place value instead. Instead of the number of sig figs. So for example, when we have these 3 different measurements and we add them all together, they go out, they are precise to different place values. And so then because of that, we always go to the one that has the least significant place value, and that would be the 10th place here, and so we'd round off using that. Now, having said that, if you're using a measuring device, say a graduated cylinder here, and that graduated cylinder is going to have markings to, let's say, the 10th place. Well, then every measurement you make with that one, you would have a measurement in the 10th place. And so then, of course, your final answer is going to end in the 10th place automatically. It's a really weird situation. Like maybe here you're using a ruler or even a more precise thing, and then here you're using a meter stick, and then here maybe you're using something like a trundle wheel, which you don't have to know what each of those are really, but they all have different precisions. Well, because of that, their uncertainty, how far off they are, is going to be different for each of those. And this just compounds the error, because say you have a ruler and the spacing between the tick marks is wrong and it gives you a number that is too high. And then your meter stick, the spacings are also off, but they're off in the opposite direction, gives you an answer that's too low. And maybe you just made a measurement mistake when you're using this one. Well, then all of those errors compound. And so it's not really worth it to emphasize this rule. About the only place where we really do a lot of addition or subtraction is when we're weighing things on a scale. For example, if you want to weigh a powder on a scale, you can't actually weigh that powder. You have to weigh it inside of a container. You can't easily get that powder off of there. So you weigh an empty container, and let's say that container has a mass of 5 grams, and then you put the powder in there, and the new reading on the scale is 5.2 grams. Well, then obviously the mass of your powder is 0.2 grams. And so then all of these go out to the same place value already, but this here would be the value that we use, and then this one here, if we're doing a multiply thing with it, this only has 1 sig fig with it, rather than the original 2 sig figs up here. Now, 1 sig fig is really imprecise, and we're going to tend to use devices that have more precision than that. We always want one that can measure to as many place values as possible, so we can have as many significant digits as possible. But again, when you are using a measuring device for the same kind of measurement every time, your place values are automatically going to end up in that same place value. That is, it always reads to the tenths, or it always reads to the thousandths place, and so then any addition, subtraction you do with that is going to end up there as well. This here is 2 more examples, and I probably should have taken the time to erase all the work there and just work it out on my own here, but anyway, you can see here that they've worked it out already, and so this one here goes out to the hundredths place, this one here goes out to the tenths place, so the final answer has to be rounded off to the tenths place. Over here, addition, it's the same thing, that we have the tenths place and the thousandths place, and so the final answer only goes out to the tenths place. That's really all there is to calculations with sig figs. It's simply a way of deciding what place value do I round to. When doing multiply or divide, it's the one with the fewest place values, and we have a final answer that has that many digits in it, that many place values in it, even if those place values are different. And then if we're adding or subtracting, we go to the one with the least place value. And then our final answer will end in the same place value. And that finishes this section.